Well, good morning, everyone, and welcome to this discussion or lecture on type wells. I've titled this as part of a series of about 3 or 4 talks that I call Type Wells You Can Count On. And this one is on scaling of production data. For those that don't know me, I'm Randy Freeborn. My job is to find out what people are doing and decide whether it should go into our software from a technical perspective, and also to do my own independent research. And what you're hearing today is some of the independent research that I've been doing. I'm a reservoir engineer. I've been practicing for decades, about 4 or more, and pipe wells and forecasting is my passion, and so you'll hear some of that today. So by way of agenda, what I'm going to show you to start with, to set the framework for scaling, is the impact that sample size has on the accuracy of building type wells or any type of forecasting you might do using statistics. Then I'll talk about some methods of scaling. What I mean by that is, how do you take a rate time profile that you have from a real well and adjust that rate time profile to different circumstances, different number of fractures, longer well length. That's the objective here. And then I will show you how you might be able to use that scaling by intuition. I call it scaling by intuition because it's really using your own sense of how the physics will change and how your results will change as the problem changes. And everyone will have their own interpretation of those physics. So that's why I call it by intuition. And then I'll show how we can use this scaling by intuition to determine some of the parameters for wells that we don't know. So if we have some wells that were cluster fracked and we've got a base case, a RTA or something, how do we take that information and make some judgment as to how many fractures we might have on a different well? So that's what we're going to talk about today. So sample size. Every time I've given a talk on type wells, there's always one person that asks the question, well, what do we do if we don't have enough wells? Or how many wells do I need to build a type well? And so I'm not going to tell you the answer, but I'm going to show you some information that might lead you to think what the answer might be yourself. So generally what we do is we say, well, let's build a type well from representative wells. What does representative wells mean? Well, in the perfect world, they're all the same length. They've all got the same number of fracs. The frac distance between fracs is the same. We put in the same amount of sand, the same volume. We're drilling in the same reservoir. And so what we do to get the same well is we take maybe a sample of 200 wells and we say, well, let's find all the wells that have the same length or about the same length. Now we're down to 50 wells or 60 wells, and then we want to get the right number of fracs, so now we're down to 30 wells, and we scale again, and now we're down to 15, and then we're down to 10, and pretty soon we don't have any wells to build our type well with. That's the problem. So what I want to show you is, how does sample size influence accuracy, and how can we get representative wells without binning? That's the objective of this talk. So let's start with a probability distribution where we have no wells at all. I just know what the probability distribution, and I'm going to pick wells off that probability distribution. So I know the right answer, and I can see how it will work out when I pick wells. So let's pick 10 wells off this probability distribution. So you can see on the purple line, that's my distribution, and those are the wells that I picked. Then we build from those. We assume equal probabilities on our probability distribution. We build, so we've drilled those 10 wells. That's a known fact, and now we're going to build a probability distribution the wells and the line, the probability distribution, is shown in yellow. And you can see with 10 wells how poorly that probability distribution matches the reality, what I started with. So now let's drill another 10 wells. So we'll keep these same 10 and drill another 10 wells, and that's what we get. Well, we're still a long way from what we started with, but look at what's happening here. Look in the middle here. We've got this huge gap between EURs. We haven't sampled in that region. Our sampling is incomplete. And now look at the purple line and look at all of the wells on the purple line. Most of them are above the P50. So I haven't sampled uniformly above and below. I've got too many above and not enough below. And that's influencing, that causes my curve to shift to the right. So let's add another 10 wells. Wow, we're starting to get closer now, but we've still got this huge gap in EUR where we haven't sampled in here, and we don't have the right slope. So let's add another 10 wells, and we're getting closer still. The gap is getting smaller. We add another 10 wells, and now we don't have as many of the big gaps in the information. And we add another 10 wells, and then we add, I think, another 10 wells. And we're up to 80 wells already, and we're getting really close to the distribution. Probably we can work with this. But look how many we have to just get the true answer. And that's assuming there's no error in how we calculate EURs. And that's assuming that we know what we're starting with. In fact, we don't know what we're starting with, and this may not be the right answer. Sorry, there's the 80 wells. Now let's put all these together in a little animation so you can see how it steps through and the accuracy changes as you add more wells. So there's the 80 wells. So the next thing I wanted to look at was, you'll see a lot of stuff in monograph 3 and that talks about the range of the mean. And the mean is the criterion as to whether you've got an accurate fit or not. And we talk about a P10 to P90 ratio, an 80% confidence interval on EUR. But what we're looking for is that 80% confidence interval on the mean EUR. But that doesn't cut it, because if you look at this slope, this here, I can have a lot of means that fit, but I may have a steep slope and a shift. And so to decide what the confidence interval is, you need to look at both the slope and the intercept, or some representation of where that line fits on the overall plot. And I use the P50 to describe that because it's something that we use a lot of time and it fits in easily. So then I took this exercise of picking some samples from a distribution, but I did it, I think, 10,000 times. So I drilled 10 random wells 10,000 times, and then I drilled 20 random wells, and I did that 10,000 times to compare what the best fit would be of both the slope and the intercept. And I'll show you this in bubbles. The bullseye is, I think, 10%, 20%, 50%, and 80% confidence interval. Anything that's gray is outside the 80% confidence interval that we like to work with, P10 to P90. So look what happens as I move from left to right, starting with 10 wells, doubling, going to 20 wells, doubling again, going to 40 wells. And each time I double the number of wells, that bullseye gets about half the size. So as I double the sample size, my confidence improves twofold. Or I can look at the opposite way. Each time I cut my sample in half, my confidence becomes half. And so that's why it's so important to think about scaling, because what's happening as we bin and we drop our sample size, the accuracy of our work using that distribution becomes poor. And if we could keep the sample size large, the concept is the error that we get from scaling is probably less than the error that we get from reducing the sample size. So if I can keep my sample size higher with some scaling, I think I improve my accuracy overall, even though there might be some uncertainty in how we do the scaling. So that's where we're heading today. And now I'd like to show you some concepts of scaling. How do we transform these old wells into representative wells? I've picked about 3 or 4 things that I think I can scale on. I think there's more, but this is a good start. Dr. Lee in his courses, if you've taken his courses in forecasting unconventional resources, he will always show you this formula. It's the formula that's used to calculate the end of linear flow or the start of boundary-dominated flow. He said, Randy, it's not that exact an equation. It's based on time for pseudo-steady state. When do you get to the boundaries? What's important is the things that most influence the time to end of linear flow is the distance between your fracs, DI, and it's squared. So if I double the number of fracs in the same well, in other words, they get twice as close, my end of linear flow is going to happen 4 times sooner. Permeability, if I double the permeability, my end of linear flow is going to happen half the time. We also have some other useful pieces of information, because often your total compressibility is the inverse of pressure. And total compressibility in this equation acts just like permeability. So pressure can be modeled like inverse permeability. And so we have a way that we can adjust and calculate. If we know some parameters on one well, we can use that to help us figure out when linear flow will end in another well that we may not have as much information for. So let's look at how we might scale for some parameters. Let's start with the number of fractures. The concept here is that while you're in linear flow, before your fractures start to communicate with one another, each well acts like a single vertical fracked well, with the exception of pressure drop in the wellbore. So as you move along the wellbore, each well will behave a little bit differently because the flowing pressure will be different by a little bit, and we'll come to that in a moment. But conceptually, each fracture is just like a separate vertical well. So if I double the number of fractures, I should double the production rate during linear flow. And so that's my scaling factor. If I double or increase the number of fractures, the proportion that I increase them by will be a multiplier to my rate. And I know that if I double those fractures and my fractures get closer, then I'm going to change the end of linear flow. So I need to make 2 corrections to the data that I have. And so let's just take an example. And the thing that says hyperbolic is a real well that I fit, and I'm just changing that to show you what the impact will be. So if I change the number of fractures from 9 to 15, I've now made my fractures much closer together. And I think that 71 should be 471, my apologies. But you can see the correction that we get to the rate. So our rate goes from 8,300 to 138.6 100,000. That's a big number, but it's the rate on day 1, or I think it's hour 1. So that's the multiplier on rate. And here's the difference on the end of linear flow. So what does that look like on a production graph? White is the base well. That's the model well that I know what's happening on that well. I know the number of fractures. I know a whole bunch of information. And so in this case, when I take the number of fractures from 9 to 15, I see a rate increase. That's the yellow line sitting above while we're in linear flow. But we start to deviate sooner because we've moved the end of linear flow sooner, and our rates will fall off sooner. Interestingly, we get less oil. So the yellow line is the ultimate recovery on the right axis from the 15 fracs, and the white is from 9 fracs. So we actually get less recovery. Well, why is that? It's because the end of linear flow is a function of the distance squared. So we're moving that end of linear flow so much further that the decline happens sooner, but much sooner, when you have closer fracs. I'll show you another one where the opposite happens, and that will help you visualize that a bit more. But I found this rather interesting. So let's look at well length now. My opinion is that I will expect a decrease in initial productivity per length of well as I increase the well length. I expect that because I'm going to have a greater pressure drop in the wellbore, so my toe will be less or more impacted than the heel. So what do I mean by that? When I'm fracking, I'm going to have much more pressure drop, and I'll be fracking at lower pressure at the toe. And so I expect to have not as good a frac. When I clean up, I'm going to have a lower drawdown or a higher drawdown pressure on the toe, and so I'm not going to have as good a cleanup. And when I produce it, I'm going to have less drawdown, so I'm going to have less rate coming from the toe fractures. Now, this isn't new. This is intuition, and it's been observed by others. Braun with Shell did a study on the Bakken, and I'm going to show you some of that in a minute. Wendy Smith-Lowe with BMO Capital Markets looked at the Montney, and she was saying, well, if you increase the well length by 70 or 80%, you maybe get 60% more recovery and more production. And so we need to sort of build that into a forecast. So the work that Braun did was really interesting. They took all of the well pairs in the Bakken, because in the U.S. Bakken, they have a bunch of wells, one-section wells, and a bunch of two-section wells. So they're doubling the well length. And they took all of the well pairs that they could find in the Bakken, and I think there was over 20,000 well pairs that they looked at. And then they filtered those well pairs until they found wells that were exactly the same as each other, except that the longer wells had more perfs, but they had proportionately more perfs. And they narrowed that 20,000 wells down to 27 wells that they said were absolutely lookalikes. And they averaged the performance from those 27 wells. And guess what? They doubled the well length, and the 180-day rate, average IP, increased from 371 to 596. So they doubled the well length, and they got 60% more productivity. So I said, well, can I use that to build some kind of scaling algorithm? And it's really simple. I said, well, I've got these 2 points in the yellow, the dots on the yellow curve, and they don't line up with 1. So if I divide those rates, the 371 and 596, by a made-up rate that is essentially with no deterioration of productivity, then those curves, that will change the curves, the slope of those curves. So all I needed to do was change them enough so that they intersect at 1. And now I have a normalizing or scaling factor that says if I have 0 well length, I have no deterioration. And I call that a well length factor. So I just plotted on the same curve what that well length factor looks, or what the IP looks like for that well length factor. I've extended this to about 2.5 mile long well, but beyond 2.5 miles it's sort of flattening, and I'm saying that's the limit that you can use this for. It's full of assumptions. I've assumed a straight line deterioration factor, and that may not be true. I don't know, but it's something intuitively that lets us scale. So let's look at the effect of scaling well length and only well length. And so I'm starting with the same hyperbolic well with 83,000 MCF a day. And I do nothing but increase the well length, I've increased the well length from 6,500 to 11,000. I've increased the fractures approximately proportional to what I've increased the well length. And so the distance between fractures remains the same. So I am not changing the time to the end of linear flow. All I am changing is the rate and the length of the well. Now my well length factor on the bottom is shown in yellow, and you can see that the degradation effect is in going from 6,600 to 11,000 feet is that you lose productivity, you lose 25% of your productivity. So let's look at that on a chart. And so here we see the increase in productivity that we expect. So that increase in productivity is uplifted because we have more fracs, and it's downlifted because I have this degradation effect going on. And I get an increase in the ultimate recovery from the well, but it's not as much as you might think. The EUR per length actually decreases by about 29% with this significant increase in the well length. And so, is it a good idea to drill longer wells? Absolutely, because it doesn't cost you much more to drill that extra length. And cost is always going to outweigh, and so it becomes a cost reduction process. But you will suffer some EUR from doing that, or I expect that you will. So now let's look at the effect of permeability. The concept here is production rates proportional to KH, but most of the time we don't know what H is because we can't figure it out from the logs. But we're also drilling wells in a geographically similar area, so the H is probably going to be similar. And so KH, we're assuming K is a proxy for KH in terms of incremental differences between wells. In a way, this is a catch-all because it can be used. We don't really know what the difference between permeability is. We can't measure it very well. And there's lots of arguments as to the ways that we measure whether a DFIT gives you the right answer or not. So it is a catch-all. It's used to match performance in one form or another. I have found that there is a relationship between the proppant placed and permeability, or it seems to act like permeability. Sweet spots will obviously have higher permeability or effective permeability. And as I mentioned earlier, total compressibility can look like 1 over pressure. So if you probably don't play much in the Eagle Ford, but the Eagle Ford has huge structural difference, and you can have 5,000 psi difference over a short distance where pressure is important. So let's look now at the example for permeability. Here we get an increase in rate in proportion to the permeability increase. I've assumed a 25% increase. I change my end of linear flow, and I'm just reporting the change in the permeability in this model. That's all that's changed. And when we look at this, we get an increase that's similar to what we saw with drilling the longer well, and we're getting an increase in permeability. But all we've done is, or an increase in recovery. So when we were doing fractures that are a function squared, so if I double the fractures, I half or quarter the end of linear flow, and we saw that we got less recovery. Here, permeability, if I double the permeability, I only half the end of linear flow. So there's a difference there, and that difference in the end of linear flow is what makes the difference between whether you get incremental recovery or not. So those are the three scaling parameters that I've proposed. I think we can maybe give some thought to a scaling parameter that looks at liquid volume on your frac that actually increases the frac length, and subject to a limit to what you can clean up, length that you can clean up and have an effective frac, you're increasing the drainage area and would increase reserves and rate at the same time. But let's look at combined scaling. So here's an example case. I say, well, okay, I've got a 9-stage plug and perf. Every fracture's perfed. But I'm going to now drill a well that has 30 stages with 2 perf clusters per stage, and I'm going to be 60% efficient. I'm going to increase the drilling length to that same 11,549 that we saw before. I'm going to drill in a sweeter spot with 25% more perm, and my sand volume is going to be 20% greater. So what does all that look like? Well, we get the rate bump. We get a rate bump of 1.5. See if I can figure out where all this stuff comes from. I get a rate bump of 4 times because of the number of fractures. I get, I'm sorry, I'm not sure. This is the well length factor. This is the well length factor, and I think, sorry, I can't remember where this comes from. I think it's from the inverse of, go back to where? I think it's the well length. It is the well length. I just didn't put the multiples here. It's 659 to 111.5. And so those are all the things that affect my performance. And when I put them all together, I've got this huge rate increase because I've got 4 times as many fracs. But in fact, the end of linear flow is causing this well to drop off very quickly. I get a huge bump in productivity and recovery, and I recover more, but not 4 times more. A lot of people think if I double the number of fracs, I'm going to double the recovery, and that's really not true. So how can we use this in terms of diagnostics? I've got 2 examples I'm going to show you, and this whole methodology has only been tested with 3 examples. So this is not widely tested, and that's why I say it's intuition. But let's see how we can use scaling to estimate completion unknowns. So why would you want to do this? First of all, you might like to know how your completion turned out. But secondly, you may have a well that you don't know what the completion looks like. So what you want to do is find out what that completion looked like, so then you can take that well and scale it to what you're going to do with your new wells. So the first example, these are Montney examples. The wells that I'm showing you are less than a half a mile apart, and they're older Montney wells, so we've got quite a bit of history on them. So my control well, the well that I know something about, was plug and perfed, 9 fracs. Every frac or every perf has a frac. They put 900 tons into this well, so 100 tons per frac was the standard design at this time. Every well was done with 100 tons per frac. And the horizontal length is 65.99. That's the same number that you've seen before in the other plots. My target well, the well that I don't understand what happened with, was completed with 5 frac stages, but it had 16 perf intervals. Each stage had 3 perfs, except for the toe that had 4 perfs. And they placed 1,100 tons of sand. So again, 100 tons per, it's not 100 tons per frac. They were obviously assuming that every perf would not take a frac. And the horizontal length is a little bit shorter than my control well. The diagnostic, the result, actually says 8 fractures were created. So let's look at the data. The red is the well that I'm trying to figure out what happened with this well. And the white represents my control well with some various scaling options. So the worst case is only 5 fractures. 5 stages, 1 fracture per stage. So that's the worst case. The best case is all 16 perfs took a frac. And that's the line at the top. And somewhere in the middle, 12 fracs, I can match the early time rates. So 12 fracs matches the early rates, but I'm not matching the end of linear flow. So let's see what I can do by playing with permeability. So I start with the 5 fracs and play with the permeability and adjust the permeability, multiply it by 2.2. I can match the rates, but now I'm too late on the end of linear flow. So it's somewhere between 5 and 12 fracs. I can probably match both. And that's what I've done. By trial and error, and it's so quick, you just click, 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 and you've got the right answer, or the best match. And so the best match is with 8 fractures. Now, if I have 8 fractures, then my 1,100 tons of proppant gets spread equally between the 8 fractures. So the number of fractures that actually happened will cause the proppant per fracture to change. So with 8 fractures and 1.35 times perm, I get a good match of the data. Interesting, the sand comparison between my target well and this well with 8 fracs says I have 37% more sand in this well. So I've got 1.35 as the multiplier of perm and 1.37 as the multiplier on productivity or on sand. And so on the basis of one well, I'm saying there might be a linkage between proppant and permeability, effective permeability, which means that you can treat proppant the same as you might treat permeability, as long as it's just the concentration that's gone up, not the overall volume. So the next example is an example where I have conflicting results. I'm using the same control well, but my target well, the well with conflicting results, 16 fracs, all plug and perf. So every frac has every perf has a frac, and 100 tons per frac. So the same sand concentration. The horizontal length is 73-75 feet. The diagnostic is going to tell you that 6 fractures were created, not 7 as you see on the slide, but it could be 7. It's close enough. And that those fractures must be communicating behind pipe. So let's look at the results. Here's a comparison of 16 fracs, 12 fracs, and 8 fracs, with a corresponding increase in sand volume for each frac. So I'm dropping my productivity as I go from 16 to 12 to 8 fracs. I'm dropping productivity because of frac count, but I'm increasing permeability, effective permeability, because my sand volume per frac has gone up. So in the early time, where I'm in linear flow, there's really no change in the rate. It's only affecting the end of linear flow and the final performance here. But no matter what I do, I still can't match the rates that we've seen on this well. So what I need to do is I need to increase the rate, which I can do with permeability. So let's see, and I would increase the rate on the 8 fracture well because that's the one that's coming closest to the end of linear flow. So that's what I can do with permeability. So I can match the early rates with 1.2 times the permeability plus, sorry, this is 16 fracs. But I'm still not getting the right end of linear flow. So now I have to do a trade-off between fracs and permeability. And so when I do that trade-off of fracs and permeability, I need 6 fracs, not 16, and 3.25 times the perm. Now, out of this 3.25 multiplier on perm, most of it comes from the sand per stage. Only 22% comes from a real increase in perm. So the only way this can happen, these are all plug and perf fracs. So the only thing that could cause the kind of performance that we're seeing on this well is if those fracs are communicating. So you frac and then you do another frac and it's intersecting and connecting to one that's already there. And that's the only explanation for this kind of performance. And so these are 2 examples that show you a little bit of the power of this kind of diagnostic approach. Now, you might not want to trust this. You might say, well, yeah, I'm going to run a simulator because I want to find out what really happened. But at least you've got a starting point for your simulator to sort of figure out what the real story is. So in summary, scaling will increase the number of analogs. We can do that because we can take wells that aren't true analogs, turn them into analogs, and use those transformed wells in our type well construction. And because you've increased the sample size, presumably you can get a net gain in accuracy. By that I mean the loss in accuracy from your intuition on your scaling will be more than offset by the accuracy that you gain from having larger samples. Scaling is really useful as a diagnostic tool. It can help you estimate unknown fracture and reservoir geometry. It can help you identify reasons for abnormal behavior. It's a starting point for a more detailed study. And perhaps the most important in today's world is it can help you estimate where the end of linear flow will happen on new wells that you drill. Because that's the biggest unknown that we have. And everything I've seen, everybody just assumes the end of linear flow is going to be the same for every well. And that's not true, and it's influencing our projections of recovery and cash flow. The one thing I haven't talked about, but I'm just going to touch in the summary, is that if we have a way to take some existing wells and change the performance of those wells to reflect completion decisions that we have, then we've got a tool to do some first-off estimates of the value of completions and how we might optimize those completions. Rather than spending a month doing what-ifs on a simulator, we can spend 5 or 10 minutes on a scaling thing and come up with some estimates of cash flow and what your optimum completion and drilling length might be. And I think that has huge value. We've done a little bit of work on that, and so far we've found that the very best thing you can do is drill the longest well you can possibly drill. That when we bracket and try and run linear programming to figure out the optimum, it's always the upper end of what we put on the well length. But it does help you play with completion design. How many fracs? What's the peak? Where do you start wasting money on frac count and stage count? And should you look at pinpoint fracking versus cluster fracking? So that's an additional value that you get from scaling that will help you in your day-to-day work and help you really maximize cash flow for your company, because that's really what your job